Good. So there's only a couple of you guys, so I'm here to answer whatever questions you've got.
For some of the questions on the multiple choice, it was like
Yeah.
asking us to pick equations that supported whatever.
Yep.
How do you know which ones would be correct?
So on those questions, I think a lot of them they're talking about which questions support like why adding drops of a strong acid or drops of a strong base don't change the pH. I think that's what a lot of them are. And so you need an equation that helps explain let me see if I can find one.
I think question 25 is one.
25. Thanks, Weston. La 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 la. Yeah. Is that what you were talking about, Jack?
Hold on, I can't see it, but yeah.
Okay. So when they're talking about why adding a few drops of a strong acid or a strong base isn't going to change the pH, we need to show what that strong acid, like what the H plus from the strong acid is reacting with to make it not be around to change the pH. And so if this H plus, this strong acid that we added in, if this H plus reacted with OH minus in that solution and neutralized to water, that would cause a drastic change in pH. But by having that H plus be able to react with the conjugate base and go and form that acid, both that conjugate base and that acid are already in that equilibrium that exists already from this buffer that we made. And so since both of those chemicals already exist in our solution, the H plus is reacting with it, meaning that that H plus is no longer just floating around by itself, able to change the pH around. That is going to help us explain best what's going on in that buffer. So I think there's a couple other problems like that that's asking very similar kinds of questions.
What would the difference between like B and D be on that then?
So B is showing that that acid is forming H plus, which it does a little bit, right? Like that's happening already in the equilibrium, but that doesn't really help us by showing that when we add H plus in, where does that H plus that we added in go? So we need the H plus to be on the reactant side. So anything else? Anything from the packet or from the free response questions or general questions about how any of this stuff works? I'm open to all of it.
Is a buffer able to be made from like any amount of concentration between an acid and its conjugate base, or does it have to be like the same?
No, it can be any concentration. The buffers that are most resistant to pH changes have equal concentrations, but sometimes let me get something that I can write on. So because of that Henderson-Hasselbalch equation, right? Sometimes, maybe we want a pH of exactly 4, but the only acid that we can get is going to give us a pH of, I don't know, like 4.2. So we can play around with the concentration of the acid and its conjugate until we can actually modify that to come out to an exact pH of 4. So we don't always need those concentrations to be exactly the same.
How would you find how many um milliliters it would take to get to the equivalence point on the titration?
All right. Let's see if I can find a question that talks about that. Here, where'd it go? Nope, never mind. All right, I'm gonna make one up. So let's say we have a question that says 40 milliliters of a 0.1 molar acid solution are titrated with 0.55 molar base. How many milliliters of base are necessary to reach the equivalence point? And say we have a question something like that. So we know that at the equivalence point, the moles of my acid and the moles of my base are always going to be equal to each other. So there's two different ways that we can work this out. One is using our molarity equation. So we know that molarity is equal to moles over liters. I know the molarity and the volume of the acid, so I can figure out how many moles of acid I've got. So if I've got 0.10 molar equals X over 0.040 liters, I see that I have 0.004 moles of my acid. And this is going to work whether it's a weak acid, weak base, strong base, doesn't matter. This part of the math is always going to be the same. So at my equivalence point, I know that that means I also have 0.004 moles of base. If I know my concentration of base and how many moles, I can figure out what volume of base I would need to reach that many moles of base. So again, I know its concentration is 0.55 molar. I know that I have 0.004 moles, but I want to know what volume. So do a quick cross multiply. And I get that X is 0.00727 liters, which would be 7.27 milliliters. So all of this sort of rests on this idea that we know that at the equivalence point, this has to be true. You also can set up, it's basically the exact same math, just putting it all into one step of saying that the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Because taking molarity times volume gives me moles. That's exactly what we did here. So we could do the same thing here and say that my molarity of my acid is 0.10. The volume I had was 40 milliliters. My molarity of my base is 0.55 molar. I want to know what volume of base I need to add in to get there. And again, these kinds of questions show up a lot about equivalence points. You can solve this for any variable, any of these 4 variables, as long as you have the other 3. So it could be that you know what volume of acid you started with, and you know everything about the base, but you're trying to find out what molarity of acid you have. All kinds of different things that you could do as long as you've got 3 of those variables figured out. Next question, anybody?
How could you calculate the initial concentration of an acid or base in a titration?
It would depend on what information was given. Do you have a kind of a problem you're looking at?
Yeah, let me try to find it. Uh, 58 on the multiple choice is kind of like that.
Okay. So 58. Okay. Oh, okay. So if you have the graph, you know the initial pH of that solution. So if I know that my solution is starting off with a pH of 12, oh, no, this is because they don't give us a KB, we can't use the initial pH, but we do know the equivalence point. So that's pretty much exactly the same math we just talked about. So at the equivalence point, I know that I used 50 milliliters of acid, and I know that that acid is 0.1 molar, and I know that I have 25 milliliters of the base. So with those 3 pieces of data, I can figure out what the molarity of that base was at the beginning. So 25.150. So I have 25 milliliters of my base. I have 0.1 molar. I just lost it. And the equivalence point happened at 50 milliliters of acid. So again, if I do that, MAVA equals MBVB, right? My molarity of my acid is 0.1. My volume of my acid is 50 at that equivalence point, because that's what the graph says. I don't know my molarity of my base, that's what I'm trying to find, but I have 20, oops, not 0.25. Come on. I've got 25 milliliters. So 0.1 times 50 is 5 equals 25x. 5 divided by 25 is 1/5. That's 0.2. So my base would have a concentration of 0.2 molar.
So I don't need to set that up and like find the PK B.
So I don't have enough information to be able to do that.
I
in
looked
this
at the
particular
graph
question.
and just found the PKB to do it though. But I got like I couldn't get the exact number because it was like 10.8 or something like that.
So, okay, so I see what you're saying. So by looking at the half equivalence point, you say that the PKB is, 10.10, 11, so maybe like 10 and a half.
The question before it said that the PKB was 10.8.
Okay. So if the PKB is 10.8, then the KB, doing this without a calculator is going to be pretty rough.
So that way just be like kind of extra, or should I just set up like the MA VA equals MB?
Yeah, because we have that information exactly about the equivalence point and everything we need to know about the acid, that's the easier way to do it. Yeah, this would be awfully hard to do without a calculator. If you had a calculator, it would be fine, and you could do the KB bit. Anything else? I know there's more of you here other than Jack. Anybody else have any other questions?
If something's a base or like a basic solution, would it still have a pH value?
Yes.
It would just be low, or low.
No, its pH would be high.
Oh, that's what I meant. Yeah.
Yeah.
The concentration of H would be.
Yeah. So remember that because we always have a pH plus a POH equals 14.
Yeah.
So if it's acidic, its pH is low and its POH is high. If it's basic, it's the other way around. Its pH is high and its POH is low.
Okay.
Anything else?
When you do a buffer,
Yeah.
if you add a strong base to the solution, the pH would go up, but if you add like a strong acid, it would go like a tiny, tiny bit lower.
Correct.
Is there a way to calculate that exactly on like a multiple choice question without the Hasselbalch equation?
Not without the Hasselbalch equation, no.
Right. Can you go over the different concentrations at like the different points in time of a weak acid, strong base, and strong base, weak acid titration?
Yeah. Yeah, let me pull up the packet so that I've got something to point to when we do this. Okay, this is the one that I like. So the one, the main one in your packet, I've got drawn out here. So that we've got at the very, very, very beginning, we've got all acid, no base, right? This, I can tell from the shape of this graph that I'm starting with a weak acid because it's got that little humpy at the beginning. So as I get deeper and deeper into this, I'm going to have more of my HA is going to start dissociating. So I'm going to get less and less HA as we go through here, which means I'm going to have more and more A minus. Right? So this says over here that at point A, we've got mostly HA, some A minus. There's no loose H pluses or OH minuses really at this point because every single H plus or every single OH minus that's getting added in is finding an H plus to buddy up with to neutralize into water. So B is my half equivalence point. At that half equivalence point, half of my acid has dissociated. So my HA concentration and my A minus are equal to each other. Anytime after that half equivalence point, I now am going to have less HA and more A minus. So that A minus is going to keep increasing until I hit my equivalence point, where all of the acid has dissociated. Every H plus has found an OH minus buddy. So my entire A minus possible is going to exist at point C. Again, there's no loose H plus concentration or OH minus concentration because they still have neutralized each other at this point. Anywhere past C, any more OH minus that I add in is excess. So I'm going to start adding in OH minus, which means my OH minus concentration is going to keep increasing. My A minus concentration is not going to change at all because I've sort of maxed out my A minus concentration until I hit sort of that maximum pH where now the majority concentration is my excess of OH minus. So if we were going to talk about doing this the opposite direction, right? If we had starting with a weak base, it's going to be pretty much the same talk, only every time instead of talking about acid, we'd be talking about base. Instead of talking about A minus, we're going to be talking about BH plus. So the base that has accepted the proton. Other than that, every single thing is going to be the same. So at the beginning, I've got all base. At my half equivalence point, my base concentration and my BH plus concentration is the same. Anywhere past my half equivalence point, I now have more BH plus than I do of base. At my equivalence point, my OH minus and my H plus concentration are the same. Anywhere past this, now I've added more acid, so my acid is all excess now until I reach down here where it's majority. Pretty much the only thing in there is extra H plus.
A minus just represents the conjugate base, correct?
Correct. The only difference if we were talking about a strong acid or a strong base, I mean, titrating a strong acid and a strong base together, is that we don't have any of that acid that stays together. So if we're talking strong acid instead with a strong base, right? We don't have that little hump on our graph. It just stays really low. It's much straighter. So anywhere along here, we have majority H plus and A minus. There is no HA anywhere in there because it all has dissociated. And then we still would have majority excess OH minus at the end. There's just no HA to talk about in there.
All right, this is my last question, I think.
Okay.
So if you're doing a strong base where it's like CaOH2 or SrOH2,
Okay.
BaOH2,
Yeah.
when it fully dissociates, would we multiply the original molarity by 2 since it's 2OH in the equation?
Yes.
So like if it was like 1 molar, it'd end up having 2 molar of H plus or OH minus.
Right. So if we have calcium hydroxide, that's a strong one, isn't it? Yeah.
Yeah.
So since it's 100% dissociates because it's strong, right? It's going to break up into calcium plus 2 and 2 OH minuses. So it's going to take twice as much H plus to neutralize that OH minus. So for example, if we had 0.1 molar calcium hydroxide, that would produce 0.2 molar hydroxide. So I would need 0.2 molar acid at the same volume to neutralize it. All right. Jack said that was his last question. Anybody else have any other questions? Going once. Going twice. All right. I'm calling it then. I will see y'all tomorrow for the multiple choice exam.